So we're going to be talking about solving, can't write, trig equations using identities today. And I'm going to put /creativity here. And by that I mean, sometimes you have to use a little bit of creativity in conjunction with the identities to put an equation in a form that it's actually easier to solve. Because you may or may not have the ability to solve an equation the way it's written initially. Now, before we get to all of that, I want to talk a little bit about where that Pythagorean identity came from. So on your formula sheet, you have all those Pythagorean identities. The most basic and most important is sine squared plus cosine squared equals 1. So where does that identity come from? And that's what we're going to look at here for a moment. And you may or may not have looked at this last year in Algebra 2. It's in the curriculum, but sometimes because of time constraints, you don't always get to talk about it. So the big idea here is let's go back to our unit circle. So I want to draw a unit circle. I'm just going to draw myself a circle. And because of the magic of technology, it's a lot easier for me to draw a circle on my paper than probably you. But do the best you can. I'm going to draw a unit circle, and I'm going to just pick an X and a Y somewhere on the unit circle. So I have a point that maybe my angle's right here. Okay, it ends right there. And I'm just going to call that point XY. And this is really similar to some of the problems we did last unit, where we were given an angle or a point on the coordinate plane. We plotted the point, drew the angle, and all that kind of good stuff. So we have this circle now with an angle theta, and we've labeled that point as XY. I'm going to do what we did last unit, and I'm going to draw myself a right triangle that uses some of the information from the ordered pair that we were given. So I can draw this right angle back at the x-axis. And what I know is that the length of this side is the same as the x-coordinate of my ordered pair. So the length of that side would be x. And then the length of this side is going to be y, because that's the same as our ordered pair, the height, how far we go up on our ordered pair. So we're also dealing with a unit circle. That's the key here. This is in our unit circle. What do we know about any radius in the unit circle? What does it have to be? 1. Yes, I saw one person. Unit circle. It's called a unit circle because the radius is 1 unit. Okay. So we have a radius of 1, meaning the hypotenuse of that triangle is 1. Now, if I wanted to, I could express the lengths of the sides of that triangle using Pythagorean theorem. So I could say, let's take y squared, which is the height, plus x squared, which is the length of the base. That's going to be 1. Right? I know that because that's Pythagorean theorem. But when we talk about the unit circle, we've also said how the x and y point could be called the cosine of theta and the sine of theta. We know that x is the cosine and y is the sine. We've talked about that. So it makes sense that I could write the ordered pair as cosine sine. I could write my sides as cosine of theta and sine of theta, because that's what x and y are. Knowing that, now the length of the base of that triangle is cosine, the length of the height of that triangle is sine, I can rewrite the Pythagorean theorem. And instead of saying y squared, I could say sine squared. Instead of saying x squared, I could say cosine squared. And this is the Pythagorean theorem, right? It's also, so now we call it the Pythagorean identity because we're using trig functions. But it came directly from the Pythagorean theorem. Like, no surprise there. If you know the Pythagorean theorem, you can find the Pythagorean identity. So that one identity, sine squared plus cosine squared equals 1, can kind of create the other 8 that you have on your reference sheet. And those other 8 are going to be super helpful as we get into solving some of these equations. So why do we even need that? Well, let's try to solve an equation where it might become a little more obvious that we need to use this. So let's solve each equation, and we'll give our answers like we have been from 0 to 2 pi. I'm going to keep using x for now, I think. We're going to use our Pythagorean identities. So first equation. Let's do 2 sine squared of x plus 3 cosine of x minus 3 equals 0. Some of you are like, oh, I can factor this. Well, kind of. Maybe not yet. And here's why. I've got a sine squared and I've got a cosine. Those aren't the same trig function. So that would be the same as if I said, hey, I'm going to factor 2x squared plus y minus 3 equals 0. And then I look at it and I'm like, nope, can't factor that. So I can't factor this as it's written, right? Because we have two different trig functions. We have sine and we have cosine, not factorable in its current state. So what I can do is think about how I can use my Pythagorean identities. So if you look at your Pythagorean identities, let's zoom in here. And I know at home you're not going to be able to see this, but if we use our Pythagorean identities, we have sine squared plus cosine squared equals 1. Right across from that, in the second column, I have sine squared equals 1 minus cosine squared. What that's telling me is that anytime I see sine squared, I can replace it with 1 minus cosine squared. Those are equivalent to each other. So if I wanted to, I can replace, and I'm going to write that here. Let's replace sine squared, this guy, with 1 minus cosine squared. Those are equivalent to each other. So wherever I see sine squared, I'm going to replace it with that expression. Well, let's do that and see what our equation looks like. So I'm going to rewrite my equation, but wherever I see sine squared, I'm going to replace it, with 1 minus cosine squared. So my equation becomes 2 times, now instead of sine squared, I write 1 minus cosine squared plus 3 cosine of x minus 3 equals 0. I took sine and I replaced it with 1 minus cosine squared. Now, when I step back and look at my equation now only has cosines in it. And that's a good thing. That's what we're shooting for. All the same trig function. It's probably not super easy to factor yet because it's kind of in a weird form. So I'm going to clean it up a little bit. First thing I'm going to do is I'm just going to distribute that 2. I need to get rid of the parentheses if I want to actually factor it. So 2 minus 2 cosine squared plus 3 cosine of x minus 3 equals 0. It's probably still not in a really great form to factor. So why don't we maybe combine some like terms? I see I have 2 minus 3. I can combine those, but that's the only things I can combine. So I would be able to write this as negative 2 cosine squared plus 3 cosine of x. Now, I can do 2 minus 3 to get what? Negative 1, right? So I'm just replacing or combining some like terms here. 2 minus 3 is negative 1. All right, now, we're almost there. At least we're almost to the point where we can factor. Some of you may not be fazed by the fact that there's a negative in front of the squared term. I hate that. I think it makes it a lot tougher to factor. So you have one of two options. You could either add or subtract everything so it's on the other side. Or I could just take this entire equation and multiply it by -1. So I'm literally just going to multiply every term by -1. Right? So that's going to give me 2 cosine squared minus 3 cosine plus 1. I just multiplied everything by -1. Okay. Yeah, now I can factor it. So if you prefer to rewrite everything with like an a instead of a cosine, that's great. I will do that. You do not have to do that, but if I were to rewrite this, maybe I call a cosine, in which case I have what? 2a squared minus 3a plus 1. That's not too bad to factor. We know it has to be 2a times a in order to get 2a squared. And then the only way we get positive 1 when we multiply two things together is if we do -1 times -1 or +1 times +1. So I think it's going to be -1 times -1, since this is -3a in the middle. And then it doesn't hurt to check, right? -2a minus 1a. And does that equal -3a? Yes, it does. So this is the same as what we get when we add those together. Okay, so we have factored it with variables. Now let's turn that back into trig functions. So 2a means 2 cosine minus 1 times cosine minus 1 equals 0. And now we're right back to something we should be familiar with, right? We're back into that idea of being able to use the zero product property and setting up two simpler equations and solving each of those. So this guy, we could add 1 to both sides, and you probably can do this just as fast as I can at this point. Divide by 2. Now we got to think about what angles have a cosine of 1/2. So what is our reference angle for 1/2 as our cosine? $60, right? So that would be pi over 3. So we're in the first quadrant because we want cosine to be positive. And then what other quadrant is cosine positive in? 4. So that's going to be what? 5 pi over 3. Good. Okay, so there's 2 of our solutions. This guy can just add 1 to both sides. Then I have to think about when is cosine going to be 1. So what angle has a cosine of 1? 0, yeah. The only one that will have a cosine of 1 is 0. We don't want to use 2 pi because that's the same as 0, and we want to keep it to just one of each angle. So pi over 3, 5 pi over 3, and 0 are our 3 solutions. All right. Let's do one more here. Bless you. Which one did I like? I like that one. So let's do 2 is 3 secant squared of x minus 2 tangent squared of x minus 4 equals 0. I lied. I don't want to do that one. I apologize. Scratch it out. My bad. I picked the wrong one. This is the one I want. And I have a specific reason for picking this one. You'll see why in a minute. Okay, so cosecant squared minus 2 cotangent equals 4. How am I going to solve this? Well, I look at this and I've got cosecants and cotangents all mixed up in the same equation. And we're kind of back in that same situation we were at the beginning of the last problem. I can't factor when there's 2 different trig functions. So I go back to my unit circle and I think about what are different ways that I could approach either cosecant squared or cotangent. And I'm going to focus again on the identity, the Pythagorean identities, because we have a squared function that we know how to replace easily using our Pythagorean identities. Okay, you can't replace just cosine with 1 minus sine. Has to be squareds. So I'm looking at that last row in the Pythagorean identities because I see cotangents and cosecants all put together in the same kind of equations. I have cosecant squared. I know that looking at my first identity in that last row, cosecant squared could be rewritten as cotangent squared plus 1. So anywhere I see a cosecant squared, I can replace it with cotangent squared plus 1. So I'm going to do that. And again, I'm going to write that down. I think it's just helpful when you look at it later to remember what you did. So I'm going to replace cosecant squared with cotangent squared plus 1. That's my goal. Okay, replace that cosecant squared with cotangent squared plus 1. All right, so what does that make our equation look like? Well, instead of cosecant squared, we're going to have cotangent squared plus 1. Okay, and that's that entire first term there. The rest of my equation stays the same. So minus 2 cotangent equals 4. That doesn't look too bad. We've got cotangents and cotangents only. That should be a little bit easier to factor. I do need to kind of clean it up a little bit, get things in the right order, move some things over to the other side of the equation because I do need this to be 0. I need that 4, the other side of the equation, to be 0. So I think about combining like terms. I only have that one cotangent squared. So I'll have cotangent squared. Then I like to put my cotangent term next. So that's minus 2 cotangent. And then let's think about combining our like terms when we're talking about our constants. So we have 1 on the left side, 4 on the right side. If I subtract 4 from both sides, I'll get 1 minus 4, which is what? Negative 3. Okay. So that's what my equation ends up looking like. All right, I just kind of cleaned some things up a little bit. I want to make it look easier to factor. And we should intuitively kind of by now know what that looks like. If you want to rewrite that, where A is cotangent, feel free. Take 30 seconds, try to factor it. I'm going to do the same thing up here just quietly, and we'll check back and see if we all got the same thing. All right. Hopefully, if you factor it with A's, you got A minus 3A plus 1. Then translate that back into cotangents. We'll have cotangent square, or cotangent of x minus 3, cotangent of x plus 1. So we've got it factored. That is oftentimes the hardest part, because now we get back into using our zero product property, which typically means our equations are a little bit easier to deal with. Not always, but most of the time. All right, so if I have cotangent of x minus 3 equals 0, that gives me cotangent of x equals 3. Now let's talk about that for a second. Yesterday, or the day before, I don't remember, we said, you know, when we end up with like sine equals 3, let's say, for instance, we said that wasn't possible, right? Because in order for sine to be 3 over 1, that meant that the hypotenuse had to be smaller than the opposite side. So we said that wasn't possible. However, with cotangent, we're comparing the adjacent and the opposite sides. There's nothing that says one of those has to be larger than the other. Okay? It can be either way. So with cotangent, there's really no limitations to what will work. Any ratio would give us an answer. The problem is 3 over 1 as cotangent is not an angle that we're familiar with on the unit circle. So if I wanted to find a solution to this, I would have to find another approach. We're going to save that for another day. For right now, what I want us to understand is I'm not saying there's no solutions possible. What I'm going to say here is that there's no solutions from the unit circle. There are solutions to this. There are 2 angles that will make this work. We just can't just use our unit circle to find them. That's all we're saying. All right, let's move to the second equation. So now we have cotangent of x equals -1. Okay, so now we have to think about x over y. When we divide x over y, we get -1, right? That's what cotangent is. Cotangent is x over y on your unit circle. So if I'm dividing two things and I'm getting 1, what has to be true about those two things?
Equal.
They have to be equal to each other, right? So I'm looking on my unit circle for a place where x and y are equal to each other. What reference angle would that be? 45s, yep, so all of our pi over 4s, but we want it to be negative.
3 pi over 4.
Good, so we're in quadrant 2, so x equals 3 pi over 4. What other quadrant?
4.
4, and what's the pi over 4 angle there?
7 pi over 4.
Good. So these are the only two solutions I'm going to be concerned with right now, because those are the two that I can locate on my unit circle. Again, I'm not saying there's not any more solutions. There are actually 2 more solutions. I just can't find them yet. I don't have the tools quite yet to find them. And like I said, we'll save that for another day. Okay, so looking at the Go formative for tonight, because I'm going to stop there for today. I think that's enough for today. On the Go formative for 5.3, you can for sure do 1 through 3 right now with what we talked about today. Those are just using your Pythagorean identities, doing a substitution, and then going back to the strategies we've used on the previous 2 days. With 4 and 5, you can try these, but let me give you a little hint. You're going to have to use some of the other identities from your sheet, your formula sheet or reference sheet, whatever I call it, to make substitution. If you can find a way to make a substitution that allows you to solve that equation, that's awesome. That's the goal. You may also have to think about, if I gave you the square root of x equals 5, what do you do to both sides to solve that equation? If I gave you that equation, what would you have to do to both sides? Close. Square it, yeah. I figured that's what you meant. Okay, that's just another hint. I'm not going to give you any more than that, but that's another hint. Okay, so you should be able to work through 1 through 3 right now. Go back and finish.